Welcome. Hoş geldiniz, welcome. Today we have the honor of hosting this event. As the moderator, I'm Associate Professor Şiir Kılkış, Science Advisor at TÜBİTAK, and Vice Chair Working Group 3 of the Intergovernmental Panel on Climate Change, IPCC. Turkish translation is available in the Zoom link that is shared in the TÜBİTAK homepage link. For Turkish translation, please select the interpretation icon in the menu. Now for his opening remarks, it is a great pleasure to invite the President of TÜBİTAK, Professor Dr. Hasan Mandal.
Okay, so dear Deputy Minister of Science and Technology, Professor Ahmet Yozgatlıgil, dear Honorable Guest, Nobel Laureate Dr. John Matter, dear good colleague of Ali Sayegh, so dear scientists, researchers, students, and colleagues and guests. So as the President of the Scientific and Technological Research Council of Turkey, shortly TÜBİTAK, it's a great pleasure to welcome you all to this interesting and important lecture. The mysteries and undiscovered truths of the space intrigued humanity of ages. The high resolution and high sensitivity instruments of the James Webb Space Telescope are enabling a better understanding of these mysteries. It's images that provide observation of the first stars, the formation of the first galaxies, and the detailed atmospheric characterization are providing many answers and opening the new questions. For example, just in the last days, the newest images of the James Webb Space Telescope discovered a new, never-before-seen feature of the Jupiter's atmosphere. The images are now allowing the scientists to measure how fast Jupiter winds change the attitude. With every new image, we gain a greater understanding of our universe. And our distinguished guest for this lecture, Dr. John Matter, has served as the senior project scientist on the James Webb Space Telescope. The scientist mastermind of the James Webb Space Telescope, Dr. John Matter, is a civil servant and senior astrophysicist in the Observational Cosmology Laboratory of the NASA Goddard Space Flight Center. He enabled the James Webb Space Telescope to look farther out in space and farther back in time, extending the scientific discoveries of the Hubble Space Telescope. I have been just learned also in his youth, he looked up to and was inspired by the theoretical physicist and the Nobel laureate as well in the physics, Richard Feynman, also representing his interest to do such fields as quantum electrodynamics. Despite his interest, his doctorate in physics from the University of California, Berkeley, led him into the observations of the Big Bang. No one knew that time that his doctoral thesis would later inspire the Cosmic Background Explorer, shortly COBE satellite, also leading to a Nobel Prize in Physics in year 2006 for the Dr. John Matter. Our guest lecturer led the proposal for the Cosmic Background Explorer mission and become the lead scientist for this mission. The team showed that the cosmic microwave background radiation has a black-body spectrum, confirming the expanding universe concept to great accuracy. Theoretical physicist and cosmologist Stephen Hawking indicated that hot and cold spot measurements in the heat radiation was the greatest scientific discovery of the century, if not of all time. Dr. John Matter then served as senior project scientist for the James Webb Space Telescope between year 1995 and the year 2023, and directly led the science team. Dr. John Matter is the 2006 Nobel Prize laureate for physics, together with the George Smoot, again from the University of California, for their work on the COBE satellite to measure the heat radiation from the Big Bang. Through our Nobel Prize laureate guest lecturer, our scientists, and especially our youth and the public as well will have an opportunity to share his great excitement for the space science. Increasing the space awareness, human capital development, and the science mission are also important pillars for our National Space Program of Turkey. This TÜBİTAK public lecture supports our space program in promoting space-related knowledge from the leading international scientists. We aim to increase the interest of a wide audience of the astrophysics, including the scientific interest in cosmic objects and the universe as a whole. With these opening remarks, it's a great pleasure to listen to Dr. John Mather to have the honor of giving this lecture on opening the infrared trajectory test with James Webb Space Telescope. So this lecture will provide the key advances that I am sure that is highly inspiring. So once more, I thank Dr. John Mather and also our good colleague, Dr. Ali Sayır, joining us this event. And of course, our Deputy Minister and all our colleagues attending this webinar meeting. So thank you and enjoying our, listening from this interesting scientific discussion. Thank you.
Thank you very much, President Mandal, for sharing your excitement. Now, Deputy Minister of Industry and Technology, Professor Dr. Ahmet Yozgatlıgil, will share his opening remarks.
Thank you very much, dear Dr. Mather, dear Dr. Sayır, dear President Mandal, and dear guests, scientists who are watching us online seminar. I'm very happy to be with you today in this very important seminar. I'm very happy that Dr. Mather is giving such a talk to us. As you all know, the technological development is only possible through a combination of strong and planned macroeconomic policies and competition-oriented structural reforms. In today's world, countries that are able to follow scientific and technological developments in the best way, internalize these developments and adapt them to their policies, can achieve an effective position in the global economy. In the 100th anniversary of Republic of Turkey, our top priority is to take steps that will reinforce our country's independence in every aspect and increase its social welfare. To this end, we formulate our policies with the awareness that achievements in the fields of industry and technology are the most decisive factor in the future of countries. In order to improve Turkey's technological competence, we continue to support all kinds of scientific and technological developments in search of the new, better, and undiscovered. The National Technology Initiative is the name of the vision that will ensure Turkey's economic and technological independence, and the conceptual definition of our efforts to maximize our ability to design, develop, and produce critical technologies and products with national capabilities. So in our 100th anniversary, we believe that Turkey's century is starting, and we would like to touch all areas in need with the multidimensional policies we have built on 5 components: high technology and innovation, digital transformation and industrial move, entrepreneurship, human capital and infrastructure. So we are laying the foundations of a strong technology-based industry with the technology-oriented industrial move, national space program, digitization, and national artificial intelligence strategy. We are creating technological awareness through major events organized under the thematic titles such as TechnoFest, Science Festivals, and Sky Observation event. In related with our strategy, today we are very honored to host Dr. Mather to give us a seminar on the interesting topic of space. And I'm very happy that we are all together here. And thank you all.
Thank you, Deputy Minister Yozgatlıgil. Dr. Ali Sayır from the Air Force Office of Scientific Research will also contribute with his opening remarks, as also the NASA liaison.
Thank you. Türk Bilim Dünyası'nın sayın hocaları ve sevgili öğrencilerimiz. Can Mather'ın konuşmasına vakit ayırdığınız için sizlere teşekkür ederim. I also would like to take this opportunity to thank Dr. Ahmet Yozgatlıgil and Başkan from TÜBİTAK to be able to create this event for the youth of Turkey. When I met was scientists who work in many years in NASA Glenn as well. When I was talking with Dr. Mathers in a dinner in a Cosmos Club with Bill Colglazier, who was the science advisor for the State Department, I was trying to tell him that the youth of Turkey will be incredibly interested to hear his perspective, vision, and what the space sciences can bring for not just one country, but whole humanity. And I do know John is an incredibly humble person. I am indebted and thankful that he accepted my invitation to give this presentation. His bio has been described by Dr. Hasan Mandal, and I'm not going to go into more details. Without further ado, I would like to ask Dr. Mathers to give his presentation, and I am again tremendously thankful that he accepted my invitation. Over.
Well, thank you very much for that lovely introduction and many introductions, and establishing the importance of science for all of humanity, and especially for our listeners today and for the citizens of Turkey. I want to tell you the story of the universe and some of what ways that we found out about it, and about the great telescope that I'm going to tell you about today. It's called the James Webb Space Telescope. Let me see if I can share my slides so you can see the pictures that I'm thinking about. So I hope you now see my screen. That I am talking about opening the infrared treasure chest with the James Webb Space Telescope. So the infrared refers to the fact that we cannot see the radiation that we're going to make pictures with, but we need a telescope that can sense infrared light. I'll show you more later about that. This project, which was launched 2 years ago almost, is a joint project of NASA with European and Canadian space agencies, and it took altogether 20,000 people to complete it and launch it into space and make it ready to operate. So all astronomers in the world can use this telescope by sending us proposals, which we ask for every year. What you see in the middle of the picture is a gigantic golden hexagon. It's made of 18 smaller hexagons, which are all made of beryllium coated with gold, and we will tell you more about that later, in order to reflect the starlight back into the instrument package. It is protected from the heat of the sun, the earth, and the moon by a large gray object that you see below the hexagon, which is called a sunshade. At any rate, it is out there and working beautifully in outer space. So now I'm going to step back a little bit and think about, why are we doing all of these things? Questions that are in my mind ever since I was a small child, although I did not know how to give technical words to them at the time. Where did we come from? Where does humanity come from? What is the history of the universe? Are there other intelligent creatures on other planets elsewhere? And where could they be? Is there life elsewhere, or is life a very unusual event, or something that will always happen given a chance? And of course, everyone wants to know, can we get out of the solar system? Can we visit other planets elsewhere? So far, we can go to the planet Mars. We could live there, although it requires a great deal of very careful engineering to do it. But astronomers can travel anywhere with our imagination. And we take pictures and then we imagine what they mean. So we'll then be able to tell you stories, and I hope some of them are true. So 2,000 years ago, people already appreciated the atomic theory. This is a poem written in Latin and translated now into English from Lucretius. This was a wonderful book which was almost completely lost to history. Medieval monks in Europe saved only one copy. They destroyed all the other copies. But at any rate, in 2,000 years ago, he already understood the atomic theory that the objects that we see are made of tiny particles, that they would stick to each other in some ways that they could not yet understand because they had no instruments, and they would grow up to be animals and plants and buildings and all the things that we see, then they would melt away. So they knew 2,000 years ago that this could be the right story. But then we all kind of forgot about that for almost 2,000 years, and we had to discover things over again. So a little bit about my history. I grew up on this scientific research facility in far northern New Jersey in the United States. This is a research farm for studying animals, for studying dairy cows to give more and better milk. My father was a research scientist studying genetics, how to breed animals to get more better milk, and how to feed them. And so that's where I was when I became inspired to become a scientist. But I did not want to study dairy cows. That study was already well in progress by my father and many other people. So I wanted to study the stars, and I wanted to understand the mysteries of the creation, the mysteries of atomic physics, relativity, quantum mechanics, as I began to learn in high school. And I thought that was the most exciting possible thing to work on. My career was going to have many random changes after that. But anyway, that's where I got started. In 1946, Lyman Spitzer was a famous astronomer. He wrote a report that said, we should build telescopes in outer space to look up as well as down, for astronomy as well as for national defense. In about 1950, this gentleman, Sir Fred Hoyle in Britain, gave the name of the Big Bang Theory to the expanding universe. And he is the person to blame for the fact that we are all completely confused about the story of the expanding universe, because it's a bad name. The idea of the expanding universe is simple, but when he gave it the name of the Big Bang, he made it sound like a firecracker, a small explosion in a space that already existed. And is completely the opposite of what astronomers have seen. Also in 1946, this boy turned up. That's me. I was born in 1946. So a lot has changed in all these many 77 years. We had just the beginning of modern technology back then, and now we have so many astonishing tools to use for astronomy, for communications, and for every other purpose of humanity. So what happened next in 1948? These men, Robert Herman on the left and Ralph Alpher on the right, calculated the history of the universe a little bit better. We already knew at that time, and I'll show you later the graph, that the universe was expanding, and they said we should be able to tell what had happened in the very earliest moments. They calculated that it should have been very hot, that the universe was filled with heat radiation, and that heat radiation should still exist to be measured. And they predicted the temperature was about 5 degrees above absolute zero, which is quite close to the actual number that we measured of 2.7. So nobody went to measure in 1948. In 1954 or so, this is the planet Mars, as people thought it was. We thought it had canals on it. And it does not, as we are surely very disappointed to find out there are no living things yet known on planet Mars. And these canals that people observed are probably due to the blood vessels in their eyes. So that was before we had photographic equipment capable of doing the work, and long before we sent probes to land on the surface of Mars. In 1957, the Sputnik was sent up by the Soviet Union, and it completely terrified the western half of the world. It was clear that the nuclear bombs could be dropped from space on anyone, anywhere, including the great, powerful United States. So we were completely angry, upset, and terrified. And so within a year, we had formed NASA, the Aeronautics and Space Administration here in the US. And just 4 years later, I have Mr. Jack Kennedy showing on the screen here. He's going to tell us that we would go to the moon, and we would do that and the other things too. Let me see if the sound will play for his recording.
But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why 35 years ago fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
So I'm not sure the sound played for you, but at any rate, I wanted to make sure that you understood. Mr. Kennedy was promising to go to the moon in 8 years. And even though we had only started NASA 4 years before that, and before that, the Soviet Union was way ahead of the United States. So James Webb, the picture on the right side of the screen here, is the man who made it possible. He had a plan, and he organized NASA, and 500,000 people in the United States worked on the Apollo program to send human beings to the moon. And in 1969, while I was a young man, astronauts actually landed there. Okay, so next screen. So how do we understand what happens in the universe, in the expanding universe? Well, number one, we need to measure distances to distant stars. We draw triangles just as people did thousands of years ago. It was possible in 2,000 years ago to measure the size of the Earth and to measure the distance to the moon using triangles. And ancient astronomers were very good at this. Then they would have also understood our other method of what we call standard candles. If I promise you that those two candles that I drew on the picture are identical, and we say that one of them is fainter than the other, we'll explain that by saying it's farther away. And now we can measure the distances to all objects in the universe by these methods. We can also measure the velocities of things. If you spread out the light of the sun or other objects into a rainbow with a very good optical instrument, quite often we'll find that there's a mark across the rainbow, either a bright line or a dark line, which we identify as coming from atoms or molecules in the object that's sending us the light. And we can understand the chemistry. We can learn about many, many things from that. For astronomers, we use it to determine the chemical composition of other stars and also to determine whether they're coming toward us or going away from us. Because if they're going away from us, the light waves arrive less often and the wavelengths appear to be longer. So now we can use this to measure velocities. So back in 1929, we got this graph. It was plotted by Edwin Hubble, and each little dot on the graph represents a galaxy. A galaxy is 100 billion stars, more or less, orbiting around a common center held together by gravity, stars like the sun. On the horizontal axis is his estimate of the distance away from us. On the vertical axis, his measurements of the velocity going away from us. And there is a big surprise on this plot. It seems that the farther away they are, the faster they are going. And if you divide the distance by the speed, you can say, how old is the universe? It's very simple. Divide the distance by the speed. So this was the first time anyone ever had the idea that the universe has an age at all, 1929. Also, you see there are 4 little dots in the lower left corner where the velocity is negative. that means those objects are coming toward us and will arrive, and we will have a cosmic collision of another galaxy with our own Milky Way galaxy. It will be very dramatic, but we won't be here at the time to watch the event. So this was understood in 1929. And by the way, it had been predicted based on Einstein's equations by George Lemaitre, and even before that by Alexander Friedmann. Anyway, they were right. Einstein was wrong. Einstein did not think this was possible. But anyway, it is what we see. So now what is my part in this world? As was mentioned, I did a graduate thesis at Berkeley to try to measure the cosmic heat. And then I got a postdoctoral position at NASA in New York City, upstairs from the Tom's Restaurant, which is quite famous in television. And I was there at age 28, and NASA said they wanted proposals to launch new satellites to do science. So I said, boss, my thesis project failed. We should try it in outer space. And he said, we will call our friends and we will write a proposal, which we did. And 2 years later, I was hired as a civil servant at NASA in hopes that this project could be built and would fly. So it did. 15 years after our first discussions, this satellite went up into space. It's called the Cosmic Background Explorer, and it had 3 instruments in it. One was my thesis project, only better, to measure the color of the radiation. One was a collection of instruments to look for the hot and cold spots, and I'll show you the map. And one was an instrument to look for the heat or the light that came from the first most distant galaxies, even if you could not see them individually. So that was the thing that flew in 1989, and it was followed up by other space satellites that confirmed our original measurements. So we're very, very proud of ourselves and delighted to have discovered something important. So here is the map that was described earlier in the introductions. This is the map of the hot and cold spots in the early universe. The universe is transparent now, mostly. Light waves can travel through space without hitting almost anything. A few are absorbed, but mostly they travel straight lines. This is a map of the universe when it was young and opaque. When the universe was young, it was hot, and the gaseous material in it was ionized. That is to say, hydrogen and helium atoms had been split apart by the heat. There were electrons and atomic nuclei, and that is a plasma, and it is opaque for light. So, however, then at this time, when the universe was 400,000 years old, it was cooled off enough that the electrons found the atomic nuclei and became neutral gas. The universe became transparent. So we see the universe as it was at that age. This is a baby picture of the universe. So why did Stephen Hawking say it was so important? Well, number one, we would not exist if there were no spots in the early universe. Gravity, operating on the dense regions, slightly denser than average, was able to stop the expansion of the material and pull it back in to make galaxies and stars and eventually planets and people. We are here because of those spots. Number two, most of the spots come from dark matter, which astronomers deduce but cannot see. Their pattern is affected by cosmic dark energy, again, which astronomers deduce but cannot see. And finally, if we ever understand quantum gravity, we might understand what made the spots. Quantum gravity is a hypothesis that perhaps space and time themselves are uncertain, just as momentum and position are uncertain for particles. Perhaps space and time are also uncertain, and that is an extremely difficult challenge for science. Perhaps some of you in the audience may solve that problem, but it's very hard. So what do we do next? Well, my chart on the left is the one where we measured the color of the radiation. We showed that the heat radiation of the early universe actually is what we said, and it matches exactly with the expanding universe picture. I got a standing ovation for showing that chart in January of 1990. On the right side, you see that I'm visiting the King of Sweden and receiving my Nobel Prize in Stockholm. So, and a totally amazing celebration of with parties and speeches for 10 days. So they know how to have a good time in Stockholm. So, however, I was already working on the James Webb Space Telescope at the time, and so I went back to work. Now we want to tell you the story of that telescope. In 1990, just a few months after the Cosmic Background Explorer satellite was launched, the Hubble Space Telescope was launched. And there it is in outer space. It's a beautiful actual photograph taken from the space shuttle. And it is just what we hoped it would be. Except one thing, when it was launched, it was out of focus. There was a mistake, a terrible mistake had been made, and it took us about 3 years to get that fixed. So astronauts went up to repair it, and they have been up altogether 5 times now to visit the telescope and make it work better and better. It is still a happy telescope, and it has many more years of life in it. But one of the first results we got when the telescope was repaired was we were wrong about our predictions of the early universe. We hoped this telescope would show the first galaxies growing from the primordial material, and we could not do it. It was not capable of seeing those objects. It's too small, and it could not see the infrared light that we needed to measure to see that most distant universe, to see far enough back in time. So astronomers wrote a book that said, this is what we need next. And they asked for the new telescope to be bigger and capable of picking up infrared light. And they also wrote, by the way, that we should develop the technology for finding Earth-like planets around stars like the sun, just in case there could be life elsewhere in the universe. So we've not done that. We've not finished that part yet, but we are working on it. And that is part of the plan for astronomy in the next few decades, to look for planets that are like Earth and could possibly be alive. So anyway, here's the result of the book that they wrote, asking for this great new telescope. So it's an international partnership, as I mentioned earlier. It is being led from NASA and with major partnership contributions from Europe and Canada. If you come to the United States and visit us, our laboratory is here in Greenbelt, Maryland, just outside Washington, D.C. The main company that put together much of this spacecraft is Northrop Grumman, and they are located near Los Angeles Airport. At any rate, the telescope is operated these days from Baltimore, from the Space Telescope Science Institute, and that is where we look to give you the pictures and the images and the data from the telescope. The telescope's about 6.5 meters in diameter. It is cold. It operates at a temperature of about 40 degrees above absolute zero, and it was launched on an Ariane 5 rocket built in Europe. We originally were promising that it would live for 5 years, and now we're thinking we'll get 20. So here's the launch. It was December 25th of 2021, and we were hoping for a 20-year life after that launch. So far, everything is working beautifully on the observatory, which is either extremely good luck or also the result of very, very hard work. Anyway, the launch is beautiful. We went exactly to the place we wanted to go. And this is the place where we've put the observatory. It's called the Lagrange Point 2. Actually, we go and orbit around that spot. Here is a diagram, not to scale, of the solar system. In the middle, of course, is the sun. You see the Earth and the moon. And the 5 Lagrange points are locations where the combined gravity of the sun and the Earth will tug the object around the sun once a year. So we can stay near the Lagrange points. So in our case, the sun is 150 million kilometers away, and the Lagrange point 2 is 1.5 million kilometers away. So it's relatively close to home as solar system travel goes. It's a perfect place to put the telescope because the sunshade that we showed you earlier can protect the telescope from the heat of the sun, the earth, and the moon all at once. Now here is our scary movie. This shows you what happened after launch. It took us 2 weeks to do what it shows in this movie in about a minute. We had to unfold the telescope, which had been completely folded up inside the rocket. First, we put out the solar panels to get electricity. We put out the antenna to talk back and forth to Earth. And now you see we're gradually unfolding the sunshades that protects the telescope from the heat of the sun and the Earth. We're unrolling the protective covers. You look at this and you say, that's extremely complicated. And it's true. But we could not find any other way to obtain the measurements that we needed to understand the early universe and to do the other scientific research that we're going to show you. So after it's all been unfolded, it's still not ready for use. It took altogether 6 months after launch before we were ready to operate the observatory. Because it had to focus it, we had to measure that all the parts were working properly and verify that we knew how to work the equipment. Because this is all done by remote control. We send up commands by radio and receive back the information by radio through a network of antennas around the Earth. So there it is in outer space, although this is how we have to imagine it, because in actuality, the telescope is in the dark. So now, why are we doing it this way? And what are we hoping to find? What have we found? We're observing infrared light. Infrared is special and different from ordinary light only in the wavelength. The wavelength of light that you can see is a little shorter than what we measure with the Webb telescope. Here's a picture of a star being born inside a dust cloud. And you can just barely see the star because there's so many glowing clouds of gas and dust around it. And the dust is obscuring our view. You might say, where does the dust come from? Dust comes from previous generations of stars, which burn hydrogen and helium and turn them into the heavier chemical elements. And then those stars explode or disintegrate, and the heavier elements come back out into space where they turn into dust grains. So space is not really empty. It's filled with gas and dust, which will then be recycled back into future generations of stars, just as we're seeing in this picture. But if we have an infrared picture, like this one, which was taken with the Hubble, you can see through most of the dust. You can see that the star in the middle is sending out jets of material, which is quite usual and common for new stars as they're being born. So we're learning how stars are born from this kind of method. We are able to see objects that are not warm enough to emit visible light. Here are infrared pictures showing features of objects that are cold, but warm enough to emit infrared light. So the actuality, it's called a planetary nebula, and we knew there was a star in the middle. Now we see on the right-hand side, there are actually 2 stars at least. And the magnified picture and the calculations and the interpretations say there really are 5 stars in the middle of this object. And they are sending out these rings and beautiful pictures of gas and dust as the stars are disintegrating, producing the dust that will be recycled into new generations of stars. The third reason we study infrared light is that the universe is expanding. We have 2 ways to think about it. One is that distant objects are going away from us, and another way is that space itself is expanding. But this is a tricky question. At any rate, we need to have a telescope that picks up infrared light to understand the light that was sent out at much shorter wavelengths when it was emitted. So that's what this sketch is supposed to tell us. An infrared telescope to see ultraviolet light when it was emitted, as we're looking at things far away and far back in time. So what have we seen? Here is the first picture we released on July 11th last year. And what we see in the picture are several different kinds of things. You see some very bright stars with the 6 spikes sticking out. We see some very, very, very bright galaxies in the middle. Those fuzzy objects right here, right here, right here, right here. Those are very massive galaxies with trillions of stars in them. And those have the curious effect of bending space-time. Einstein told us that light can be bent by passing through in the area of a gravitating object. So it was the first proof that Einstein was right, that light would bend passing the sun. Here we're using that fact to magnify the images of much more distant galaxies. So these strange-looking curved objects, this pink one, this pair of pink ones, this strange distorted image, many of these are highly magnified images of very much more distant galaxies. So we are using nature's lenses to extend the power of the Webb telescope. So this is why this is my favorite picture of that we've gotten all along. It proved the telescope was working beautifully, and it's full of new scientific discoveries. I'll show you a little bit. So the first question, well, what are those first galaxies growing? And so we hunt for them in the big picture. We look for things that have odd colors to say that there really could be very, very distant, very far away, very far back in time. And then we magnify the pictures as much as we can, and we get a spectrum of each of those little fuzzy objects, and we stretch out the light into its rainbow to do the chemical analysis and measure the velocity of going away. So the answer seems to be these very first objects are much brighter, much hotter, much more mature than we expected them to be. So this is not the first time astronomers have been wrong about something we predicted. And it's one of the things that makes astronomy exciting as a science. It's very much an observational science. Everything is a surprise. Here's a beautiful picture close by galaxies that are in the process of merging together. The one on the left is very nearby. The four other ones are going to be turned into a single large galaxy in a few 100 million years, because you can see they're falling towards each other. The top one has a black hole in the middle, and we're able to observe the motions of gas and dust orbiting around the black hole. And we're beginning to understand how do the black holes grow. So we discovered with the Hubble Space Telescope that almost every large galaxy has a black hole in the middle. And that was a big surprise. Now we say, how did that happen? Did the black hole form first and then produce a galaxy? Or did the galaxy form first and then produce a black hole? So this is a question we're serially still working on very hard, and we don't have the answer for you yet. You can see in this picture the results of a collision. This arc of pink area is due to new generations of stars that are being born because of the collision. Here is a picture called the Cartwheel Galaxy. The story is that the small galaxy in the upper left actually passed right through the center of the large one, and we're seeing a splash, the result of material expelled by the collision from the big galaxy. And these are new stars that have just been born in the outgoing gaseous material. So we're using this as a star formation laboratory to understand how this can happen. We are looking inside galaxies. This is a picture taken with the longer wavelength coverage that we have. And you see this galaxy appears to have holes in it like a sponge. So the reason for this holes in the galaxy are similar to the reasons why we have holes in sponges. The gaseous material that blows up a hole in a sponge as it's being manufactured is like the gaseous material in this galaxy. And where does that gas come from? This is from new generations of stars that have just been born in these places which are now appear to be empty. So the energy heats up the gas, pushes away the material, and pushes the empties out that piece of the galaxy. We are looking at places where stars are being born today close up. This is a place in the sky we observed with the Hubble telescope. It's called Pillars of Creation. And now we can see with the infrared capability many, many more details. You can see pretty clearly that there's a wind blowing through space. And what makes the wind? Previous generations of hot new stars were born up in the upper right corner outside the picture. And in what we see here are little knots of dense regions. Here's one where you can see a new star has just been born in this little spot. So this is another star formation laboratory. We want to know how stars like the sun are being born. And there are hundreds of them inside this cloud to study. You can even see this little area of bright red, which is some of the radiation from the new stars is peeking out. And so just learning to how does this work? We have a remarkable image of a single star being born, what looks like a hamburger bun. This we think right here, this dark area is a new solar system being born, and we see it edge on. We think there's a star right in the middle. We think there's an orbiting collection of dust and gas and planets in this general area. The starlight is escaping and going up and down and illuminating the remains of the cloud from which the star is being born. If we come back in a few 100,000 years, most of this dust will be gone, and we might be able to see individual planets in this area here. They're quite common, as we know from most stars have planets. Most stars have many planets, which is a good big discovery of the last few years. We have recently discovered, this is a very new discovery, that sometimes we find pairs of objects that are a lot like planet Jupiter. So how do you find them? Well, you take a picture of the Orion Nebula. You all can see the Orion Nebula if you can go out of town. This is the middle star of the Sword of Orion. The constellation of Orion is actually not a star at all. It's a cloud with many stars in it. And so what they did was they took a picture and they noticed these double objects. This one, they expand the image over here, two objects that seem to be about the size and mass of Jupiter, which we can tell by calculating their spectra. Anyway, there they are. We do not know how this happened. We know planets form in orbit around a star, but how does a planet form without a star? So that's a big mystery for us now, and something maybe we will be able to work on. So this is a project for future students of astronomy to work on how are the stars born and how are the planets born like this. Everyone wants to know, are there planets around other stars and are they like home? This is the method we are able to use with this telescope. When a planet passes in front of a star, the star appears to get fainter for a while, maybe a few hours. And if it does it again every few days, we say, okay, we know how long it takes for the planet to go around the star. We can calculate the size of the planet as well as the temperature of the planet. And now the next step begins. Does the planet have an atmosphere? If so, then some of the light of the star would go through the planet's atmosphere on its way to our telescope, and we would be able to notice this. So the answer is yes, the technique works beautifully. Large planets like Jupiter or Saturn or Uranus or Neptune, when they pass in front of the star, they show us that there's an atmosphere with various kinds of chemicals in it. Ammonia and methane and carbon dioxide have been seen out there. Even atoms of sodium and potassium have been seen in these other planets. But the small planets, the size of Earth, so far they have found none that have an atmosphere. This is not exactly a surprise because the stars we're able to observe in this way are hostile. They send out blasts of magnetized plasma every few days, and that could remove the atmosphere of a small planet. Well, on the other hand, they're there, so we would like to know more. So that's how we look for planets and planetary atmospheres and the chemicals in the planetary atmospheres. Here in the solar system, we study the ones that we already know. There's beautiful Jupiter with a ring. You can see there's a ring around Jupiter, which is almost impossible to see other ways. There are many, many, many satellites of Jupiter. I think there are well over 100 of them have been counted now. Jupiter has an aurora at the north and south poles. And by the way, the red spot isn't red when you can't see with your own eyes. This is an infrared picture. Of course, we have to substitute colors when you can't see the light at all. Big and beautiful, and one of these days we will understand much better how Jupiter works, and especially how is it possible that that great spot, which has been observed now for 400 years since we first pointed a telescope at the sky, that red spot has been there the whole time. It has changed a little bit, but what's making a red spot? We actually observed attacking an asteroid. A little while ago, we sent a probe to a double asteroid, and we dropped a large piece of metal into one of them, and we wanted to see what would happen. So we watched them with all the telescopes we had. The Hubble telescope could see it, the Webb telescope could see it, and the answer is that a lot of debris comes out of the collision. And we're able to measure how much does the asteroid move, how much is it deflected when we hit it with something. This is something we need to know because we need to protect planet Earth from killer asteroids. As you all have heard, a killer asteroid struck the Earth about 65 million years ago, and it was a very bad day for dinosaurs. And the mammals, our ancestors, survived. So we are here because of that. On the other hand, we don't want another one to destroy our civilization. So we are getting ready to protect ourselves from asteroids. And this is one of the ways. We have observed the satellite Titan. Titan is a satellite of Saturn, and it has a surface of solid ice, possibly covering a liquid water ocean. On the surface, there are lakes and rivers of methane and ethane, hydrocarbons, that we would use for fuel here on Earth. But of course, it's too cold out there. The temperature is so cold that only a few molecules could possibly be in the gaseous phase. So there's lakes, rivers, rain, clouds, weather, all kinds of things on the surface, and it's a fascinating place. So we are sending another probe out there, and this time we will land with a helicopter and be able to fly around from time to time on the surface of Titan, looking for signs of interesting geology. And of course, everyone wants to know, is there another possibility for a life form? And I don't think this will be it, but you never know. We would be looking for signs of interesting chemistry. We have looked at Neptune. Neptune has rings like the other outer planets do. There it is with the satellites named after Greek mythology. We have a picture of Uranus, another of the giant outer planets. This one has satellites named after Shakespearean characters. This is unique in the sense that we can see the rings head on because, as it happens, Uranus is the only planet with a spin axis that's not perpendicular to the orbit plane. So because of that, we're able to look in on the pole and try to understand the fascinating properties of this amazing planet. So there are so many more things to tell you about, but you can follow us on the internet, or if you just do a Google search every day for James Webb Space Telescope results, you will find many amazing pictures every day. So maybe I'll conclude here and be happy to have questions from our audience. Thank you very much for the invitation, and I hope you will come and join us and do some science and engineering.
Thank you. We thank Dr. John Matar for his highly inspiring presentation. We had the opportunity to better appreciate the building stages of the James Webb Telescope and what has been learned so far. So we have quite a number of questions for you, Dr. Matar, based on your presentation. We have clustered this into some like scientific process, the observations, and other questions. So let me first start. That is a question directed to you. What did the Nobel Prize mean to you? And do you think that you accomplished the top work that you could when you heard that you received the Nobel Prize?
Oh, my goodness. Well, the Nobel Prize meant to me that our team had done good work and that we had been very fortunate that the universe yielded up a secret for us. So we were very proud of our accomplishment and we were proud to be recognized for the accomplishment. But I think we all knew when we started that this was a possibility. So what have I done since then? I have continued to work on the Webb telescope. That was my main mission, and it still is. And what are we going to do next? What are the future observatories that we could build?
And related to your answer, we have one more question. It's related to the topics. What is the most important topic that humanity must be working on in the field of astronomy and astrophysics? So to follow in your footsteps, what is your recommendations? Oh,
my goodness. Well, astronomers write a book every 10 years saying this is our top priorities, for where we think the best new subjects are. And the ones we're working on already with the Webb telescope are pretty important. The origins of the galaxies, the formation of the black holes, growth of stars and planets. Are we alone? Is there life elsewhere? But there are also some huge mysteries. The dark matter, the dark energy have been deduced by astronomers. Nobody can see them. We need to know more about them. Eventually, in physics, quantum gravity is one of the great challenges. It's a theoretical possibility. There is such a thing. We may or may not ever get any observations that will tell us what to do. But more ideas, more clear thinking may be helpful in that area. So many, many wonderful challenges. As you know, astronomy is an observational science, so everything is a surprise.
Thank you very much. So you also provided some problems still in the future, including the quantum gravity. We have one question that does relate to the observations. It's asked, is it true that the Big Bang did not start in one point, that it occurred across the universe or dark matter? What are the newest observations on this question from the James Webb Telescope?
The Big Bang is a misleading name for the expanding universe. The expanding universe all expands at once from the, it was not compressed into a point. It was highly compressed, but has always been infinite. When it was young, it was infinite. It is infinite now. We cannot see all of it, of course, because it has an age. So light travels at the speed that it has of 1 light year per year. So we cannot see all of the universe, but we imagine that it is actually completely endless, infinite, and always has been.
Thank you very much, Dr. Matar. It's always important to align the equipment that you need on the telescopes with the scientific objectives. So for example, on the James Webb, you have the cryogenic temperature telescope and instruments for the infrared performance. We have one question that is trying to, I think, represent this. It's asking, what is the hardest part about building the telescope according to you? How do you align it with what you want to measure, how to measure it? So this process of what is the hardest part of building telescopes and how did you overcome them?
Okay, well, the first thing to decide is, why do you need a telescope? But what is the discovery you hope to make? And so for that, we consult astronomers, and they say, this is important. This is what we would need to make a discovery. And then we say, okay, engineering teams, can you build that? And they say, well, not today. We need to develop something that we don't have. So we realized we needed to invent 10 new technologies, including better detectors, ways to polish those mirrors, ways to cool the telescope down, some cryogenic electronics, things we had to invent before we could actually finish the design. And then we held a design competition. We sponsored studies by two great aerospace corporations and their teams to say, how would you do it? And they wrote huge books of plans and proposals. So we could do this for you. And then we had to choose one. So that's how we go about designing the world's most powerful telescope. No one says, I know how to do it. We have a competition.
Thank you very much once again. So you mentioned in your presentation, it's a 5-year space mission with a 10-year goal. I think the next question is relating to this. What are the foreseen properties and goals of telescopes that can still be sent out to outer space? Are you in the process of collecting those competitions currently? And if so, could you share them with us?
Yes. One more telescope has recently been launched from Europe. It's called the Euclid mission. It's looking for the dark matter and the dark energy, or I should say looking for evidence about them. The NASA is going to launch one in 2027. It's called the Nancy Grace Roman Space Telescope. It's named after our first astronomer and head astronomer at NASA. It's going to also look for the dark matter, the dark energy, and also planets around other stars. And will survey a large amount of the sky, looking for strange and unusual events. We have our little book of wishes from the decadal survey, we call it, that calls for basically 3 kinds of new observatories. One would look for planets around other stars like the sun, and that would be the highest priority, the next one to do. Then also an X-ray observatory to look for the extreme temperature, high objects like black holes and all kinds of extremely high exotic processes out there. Then there's also a far infrared telescope that would pick up even longer wavelengths than what we can pick up with the Webb telescope. So there are 3 giant observatories that have been proposed, and all would be exciting. I think it'll take us about a century before we're done with the construction and use of those 3 telescopes.
Thank you very much. We have a technical question. How do black holes reach thermodynamic equilibrium with the galaxy instead of swallowing it?
Oh, my goodness. So, material falls into a black hole when it gets close, but it has to get very close to a black hole to fall in. Has to be aimed right in. So ordinarily, a black hole can sit in the middle of a galaxy and nothing will fall in unless it happens to be aimed in the right direction. So what happens quite often is gaseous material is pulled in toward the center. It orbits around the black hole, and when it is gradually able to leak into the black hole. So we see this. We see gaseous material compressed to high temperatures and pressures, and we're able to observe that part. Once in a while, we see a star falling into a black hole, and we see the star being turned into debris on the way in. So this is called a tidal disruption event. Once in a while, we see a black hole fall into another black hole, and small ones, the mass of ordinary stars, have been seen to do this using the LIGO observatory. We can't see that easily happen with supermassive black holes in the centers of galaxies, but we certainly expect it must happen. So it's a very wonderful challenge to understand that one. So students, a good challenge for you.
Thank you, Dr. Matar. Maybe you answered this, but we have one question regarding what you think is the most logical in the sequence of the black hole in the center in the galaxy, and then the galaxy is forming. So what do you think is the more logical in the sequence of the black hole or galaxies? So this is, if you want to add anything, we have one question like this.
Okay, well, I'll give you my guess, which is that ordinary stars, very massive ordinary stars, can become black holes in a few million years. A star of the mass of 100 times the mass of the sun will burn out and turn into something in about 3 million years. So that's a way that we can get lots of small black holes. And I think there must be a way for the small black holes to find each other and grow into bigger ones. Then there's also the challenge of how does gaseous material fall in? And so I think the first black holes were stars that blew up, and then that became the nucleus for the larger black holes. But that's not my subject matter. I'm not an expert, so I think other people will have a different idea.
Thank you very much. We have other questions. I will try to summarize those questions. So what are your recommendations for becoming an astrophysicist? And what are your recommendations for space astronomy lovers in Turkey? And how to better connect findings from outer space into related policies? So,
oh my goodness. Yes. 3 wonderful questions. So, how to become an astrophysicist? Well, I think we astronomers need to study every kind of science. We need to know physics, of course, a little bit of relativity. We need to know a little bit about everything, because almost all the laws of physics are needed to understand how stars and galaxies grow. It's very complicated. We need really good skill in computer science, because we use numerical simulations. Similar to what we do to predict the weather, we have hydrodynamic codes that represent the motions of gases in the presence of magnetic fields. So computer science and studies of all branches of physics are related. If you want to be an astronomer who builds things, then you need to study some engineering. Engineering, as you can see when I introduced the project, 20,000 engineers and technicians built the Webb telescope. So we need many more engineers than we need scientists. So any kind of engineering is of value for space projects. For public policy, I think we can all see that there's a scientific and engineering component to every problem. When we say the Earth is getting warmer, we say, well, what are we going to do about it? We need to measure that it is, and we need to, similarly, we need to invent solutions such as electric power for everyone. So investment, public money and private money into electrifying the entire world is a huge thing that's happening right now. So I don't have to tell you, because everyone can see now, that electricity from solar and wind and water power is cheaper than coal and oil. So we should just do that. And we are doing that much more quickly than people expected. So, so many, many public policy things that we can get from space. Of course, NASA and other organizations, we now observe the Earth from above. So we can see and show people how the air is moving, how the water is moving. And it's hard to avoid understanding that you have to do something.
Thank you, Dr. Matar, for your insights, your scientific insight on this matter. We have 2 questions. Maybe you would like to answer them together. One is asking, does the expansion of the universe in time and space, does this change some changes in the formula in physics books? And we had one question that, do you believe 100% in the space-time theory of Einstein? It would be great to hear directly from an expert scientist.
Oh my goodness. So I think the question of the expanding universe has not been changed by the Webb telescope observations. Everything that we see fits perfectly with the original story of the expanding universe. We have not yet changed the age calculation, but we do have a wonderful mystery of what is that age. There's a number we call the Hubble constant, which is the slope of that curve that I showed you of the velocity versus the distance. And we have different groups getting different answers. So this is a wonderful puzzle for astronomers right now. Either we've made a mistake or there's something strange happening that we didn't expect in the universe. So that's a lovely challenge to have right now, and the Webb telescope will help answer that one.
Greatly said. I remember reading that Hubble constant may not be a constant and how this can be different. So there is definitely a scientific question that can be asked. We had one question talking about the scientific process. How is it possible to isolate data in outer space because it's not a closed environment? And are there uses of this question was asking about the proton accelerator, but maybe you can make this question related to this, but it's asking, so how do you isolate the data that you're searching for in outer space in this open environment and extract the data that's useful for your scientific questions?
Okay. Well, what we're doing is we're taking pictures, photographs, and most of the things that interest us are galaxies or stars, so they look like little dots on the picture. And so it's not too hard to say there's a difference between that object and the sort of uniform cloud behind it. So the sky is a little bit bright, but we can see that there's what we call a background light that comes mostly from interplanetary dust here in the solar system. It's lights up because the sun shines on that dust. So there's a kind of glow, but it doesn't have objects in it. It doesn't have stars and galaxies. So we just take a picture and we say that thing over there, that's what we're looking for. So that's how we separate the near and the far. Could you remind me the other question?
There was a question about a proton accelerator, but I think it might be maybe research later after this presentation. So we have many questions. I'm not able to cover maybe all of them, but at least we tried to group these questions when we were asking to them. In this sense, I would like to ask you if you have any other remarks that you would like to make, any other recommendations, insight on possible discoveries that we received the last image from James Webb on October 19th, but are you expecting, what will be the next image?
Oh my goodness. I guess one of the most important observations is that we have demonstrated that the entire world can combine forces to build something extremely complicated and make it work. So we should be optimistic about the capability of human beings to solve problems. Engineering problems can be solved if we agree that we want to solve them. So I think optimism towards our future is a very important lesson that we can get from this success. So that's, I think, number one. So we should interpret that to say, have courage, identify the things we need to do, and just do them. So we can cooperate internationally to do things. Despite many current affairs, we should be optimistic and look for ways to do things together also. So I encourage all of the students to take the challenge and understand how to connect science and the public policy issues of today. There's an opportunity as well as a responsibility.
The perfect opportunity and responsibility. So having optimism for the future, having courage and collaboration. Dr. Matar, thank you once again for your wonderful presentation on opening the infrared treasure chest with James Webb Space Telescope. We do have one additional question to Professor Dr. Hasan Mandal and Professor Dr. Ahmet Yozgatligil. It is asking, what are the priorities of our national space program, like human capacity, and how do you see the future of our national space program? So I would like to ask you also for your closing remarks, President of TÜBİTAK, Professor Dr. Hasan Mandal, and Deputy Minister, Professor Dr. Ahmet Yozgatligil.
Okay, so Ahmet Hocam, maybe you are responsible from the Space Agency, so maybe you are the right person to tell about, to answer to the question on our national policy.
Thank you very much, Dr. Mather. It was really excellent. I listened, with great interest. As Turkey, we have established our Turkish Space Agency in 2018, and then we have established our national space program, including 10 important goals. So I would like to mention some of them. We are sending our first, let's say, human space traveler to International Space Station in 2024, January 2024. He's gonna be doing a scientific mission. He will do 13 different experiments, and also we have a moon program. In 2026, we are planning to reach the moon with hard landing, and later we are also planning to continue further by sending a rover to the moon. And also we have other programs. I mean, space economy, the new space concept is our interest, nation's interest, and we'd like to have our own access to space. So we have a lot of things to achieve, and we are hoping to achieve this with the youth that are here today listening to you, Dr. Mather. Maybe listening to you also inspire them to become an engineer, astrophysicist, and let's say space enthusiast. And I would like to thank you again for that. Also, I would like to thank TÜBİTAK and Professor Mandal for organizing such an event with reaching actually at least 1,000 right now, and many thousands after we publish it alive. I mean, we publish it on YouTube. And also, I would like to thank Dr. Ali Sayar, who is really, we organized this with you, and we are really thankful for his support, not only for this presentation, but also for many scientific programs and collaborations to Turkish community. Thank you very much.
Yeah, so I also say maybe some closing remarks from the TÜBİTAK side. So, I mean, first of all, answering the question, I mean, as a complementary to the Professor Yozgat Ligel as our Deputy Minister. So, yes, indeed, now we have our plan. I mean, has been addressed for the 10 missions. And most of them, of course, are relating with the science and technology based. So therefore, the TÜBİTAK is one of the main actors in that respect, both for the as a technology provider. I mean, our observation satellite for the high resolution with the submeter has already been now in mission. Was launched in the last April 15, and now is on mission. The name is IMECE. Is 90%. I mean, it's 100% is designed by us, and 90% of the components are designed and developed and produced by our own researchers and engineers. And next year, on year 2024, we will be launched our communication satellite. It's the Turksat 6A, and this will be our first satellite, which will be again designed and developed and produced by our Turkish researchers and engineers. And also already been mentioned our Deputy Minister that rough landing and with our own vehicle. So this is not only a kind of a mission, but I mean, we have been designing our own vehicle as well. So, and also I think one of the important component is the human capacity. So I can see that the number of interests to do this webinar, both on Zoom and also in YouTube site, and also you can also acknowledge and consider on the number of questions and the quality of questions, and many of them is coming from our youth and the young generation. And every year we are having, starting from year 2018, we are having a festival, so-called the largest festival in the world, in the globe, is the Technofest. This year, 3 million people are attended. 1 million students are the contestant for the 41 different type of competition. So therefore, our strength and motivation and also the responsibility is our young generation. And in this remark that your attendance and your presentation and your contribution, and especially the answers are given from different type of an area. and your remarks are very valuable. And I learned myself as well during this 1 hour time. So once more, thank you very much, and looking forward to seeing you physically next time in Turkey. And by this way, I also thank again our good colleague of Ali Sayır. Make the right interface to introducing you to us. And of course, we will keep in touch with him. And also I thank very much to Professor Ahmet Yozgat, our Deputy Minister, who also is a big contributor to this event. And the most thank is, our kind regards are coming to do our, colleagues who are attending this event, this meeting, and especially the youth students, our next generation. So once more, thank you very much for all of you, and looking forward to seeing for you in another event, either physically or another online event. And thank you, and good afternoon and good day from your side. Yes, thank you very much.
Dr. Can Mathers, Can, you make my day, and I am extremely happy what happened. It was beautiful, and you give one of the best presentations that I ever heard. I heard a couple of your presentations. It was incredibly clear. But you give this presentation on the 100th anniversary of the Turkish Republic in 2023. It means a lot for the Turkish people, especially just like my colleagues, Dr. Mandal and Yozgat Ligis stated. It was great for the youth of Turkey. And I do not believe the Turkish Republic will leave you alone. They will follow up with you. They have a great societal obligations and ethos how to deal with the guests. You will be a wonderful guest in the future Turkish event. And in that regard, I also take this opportunity to thank Dr. Şiir Kılkış. She did an unbelievably good job on the question and answer sessions. I was very impressed. As Dr. Mandal stated, it's not just the presentation, the quality of the questions and how the communication occurred is going to have enormous amount of momentum for this Turkish scientific community. Thank you, sir. Thank you. You're making my day.
Thank you for the invitation. It was a great pleasure to talk with you, and looking forward to a great future together.
Thank you. Thanks a lot. Okay. Yes, we can finish up our technical team so we can close the session.